Assalamu alaikum warahmatullahi wabarakatuh. Friends, today we will discuss TL494 pulse width modulation control circuit, PWM control circuit. I received a lot of messages. Sir, make video on 494. Sir, make TL494. TL494. I have lot of comments, lot of messages asking about TL494. I will request you to subscribe my channel. If you have not subscribed, subscribe it. After watching this video, if you have any comment, any suggestion, please write in the comment box. And how you find this video, please write your feedback. I will thankful. TL494 basically is SMPS pulse width modulation control circuit. It have two error amplifiers, two different error amplifiers to monitor different values, voltage, current. Pin number 1 and 2 is inverting and non-inverting, 16 and 15 inverting and non-inverting for second amplifier. This is error amplifier number 1, error amplifier number 2, and here we have feedback compensation pin. Then we have dead time control, pin number 4. Pin number 5 is CT, RT, timing capacitor, timing resistor. Basically, these two components are used to program the frequency, and this is used to provide a dead time between switching of two different channels. What are channels? We will see. Pin number 7 is ground. It is power ground. Pin number 8, collector. Pin number 9, emitter. 11 and 10, emitter collector. These two are channels. These are switching transistors. This IC is open collector, open emitter based. So we can say it is working like a switch. If we apply something at emitter, we will receive from collector, or if we will apply something at collector, we will receive from emitter. So it is working as a series switch. The base of this transistor, these transistors will control from this PWM control section. Then we have VCC. So this IC normally 15 to 40 volt, and up to minimum level is 7 volt. Then we have output control. Then we have V reference voltage, this 5 volt reference. When we apply 7 volt at VCC, it will generate a stabilized 5 volt reference. It is in 16 pin DIP and SO16 package, that is SMD. It is its simplified diagram. We have error amplifier number 1, 2. Reference is connected in this shape. When we connect 12 volt, we will take 14 at pin number 14, 5 volt reference. Here is control. This control will drive the both transistors, both switches. It is some clear diagram. Here we have oscillator section. Here we have dead time control. So basically its working principle, it is fixed frequency oscillator. This IC can be programmed to operate at 1 kHz to 300 kHz. But when we set a frequency, after that it will work at that frequency. It will not change frequency, it will change its duty cycle. What is duty cycle? For example, we calculate some components to produce 10 kHz. So we will connect components here. So this IC will switch at 10 kHz. 10 kHz mean 10,000 repetitions of on and off. This is called one repetition. This is T. From this point to this point, it is called one cycle. From this point to this point, one on and one off pulse is called 1 Hertz, one cycle. So this cycle will repeat 10,000 times if we have 10 kHz frequency. 10 kilo means 10,000. So 10,000 repetitions on and off. But in each cycle, how much period will be utilized to turning on the transistor and how much time it will remain off. The ratio between on and off is called duty cycle. So here it is called 25% duty cycle. So this IC will work 25% on in this case and 75% will off. And in this case, if it will increase its duty cycle, how it will increase its duty cycle? It will depend upon the feedback. This feedback will apply to this control section, so it will adjust the duty cycle to increase or decrease the output voltage. If we say 50%, so 50% on, 50% off. If we say 75%, that means 75% from here to here on, and from here to here off. 25% off, 75% on. If we say 98% on, so from here until here it will remain on. Just only for 2% of the time will off. So it is called duty cycle. It is called PWM, pulse width modulation. So it will modulate the pulse width. It will change its duty ratio. Some highlighted features are here. It is fixed frequency, PWM control, as we discussed. So on-chip oscillator with master and slave operations. We will see it in detail. It have on-chip error amplifiers, as we discussed, on-chip 5 volt reference, adjustable dead time control. So we can adjust, we can set the gap dead time between the two channels, channel A and channel B. And channel B to channel A, dead time control will be allocated. Then we have 5 milliampere source or sink current for both transistors. So this IC have a very special function that is called push-pull or single-ended operation. This IC can be programmed to operate one by one. This will on, this will off, this will on, this will off, vice versa. If this will on, this will off, then this will on, this will off. So they will work opposite to each other by controlling this pin. Then we have under voltage lockout. As I discussed, we can apply up to 7 volt minimum. Minimum level is 7 volt, but at 5.5 volt this IC will make under voltage lockout for more protection. Then we have another model of this IC that is called NCV. We are discussing TL494, but if it is NCV, that is for automotive and other special functions, but we are discussing TL494. So if NCV 494, that means all these parameters will be considered for that IC as well. Where it is used? It is used in most of commercial IC, commercial circuits, in PCs, microwave ovens, in solar inverters, power inverters, e-bike chargers, washing machines. Its pin layout, and this is footprint of these pins, pin number 1, 2, 3, 4, and here is pin definition, type. In this portion, if we see, here is mentioned type. I, that means input. So I, input. O, output. This dashed, that means it is common pin. So CT is common pin. Ground is common pin. RT is common pin, and VCC is common pin. So reference, it is out. E2, E1, C2, C1. This is output. So pin number 1. Its abbreviation is here, 1 in positive. 1 in positive, that means non-inverting input to error amplifier number 1. 1 in negative, that means error amplifier number 1 inverting input. 2 in positive, 2 in negative, inverting and non-inverting inputs. C1, C2, collector terminal for BJT, output BJT. Here, pin number 11 and pin number 8. Pin number 9, 10 are emitters. Then we have recommended chart. Typical 15 volt VCC can be applied up to 40 volts. But minimum level we can apply up to 7 volt. So collector output voltage from typical 30 and maximum 40 volt we can apply to collector. Then we have collector current 200 milliampere. Then we have amplified input voltage. The voltage applied at collector -2, VCC -2. It can be applied to amplified input voltage. VCC -2. The applied VCC less than VCC 2 volt. current into feedback terminal, that is 0.3 milliampere. Reference output current. So this one is feedback current. So this one is reference, this output, and this one is input. So here it is 10 milliampere. So timing resistor can be used from 1.8 kilo ohm to 500 kilo ohm, and capacitor 0.0047 to 10 microfarad. In the old data sheet, it is 1 kilohertz to 200 kilohertz, but in new data sheet that is updated in 2017 from on semiconductor, so that is up to 1 kilohertz to 300 kilohertz. In previous it was 200 kilohertz, but now in new data sheet it is 300 kilohertz. Operating free air temperature. So TL494 is 0 to 70 degree and 491 is minus 40 to 85 degree centigrade. Then we have oscillator section. If we connect CT 0.001 microfarad and RT 30 kilo ohm, then it will operate at approximately 40 kilo ohm. Standard deviation frequency at CT this and RT this. So F oscillator deviation, that is 3%. So frequency change with VCC. If we jump VCC from 7 volt to 40 volt, so delta change in oscillator frequency at delta change in voltage, that is 0.1%. And with change to temperature, it can deviate frequency up to 12%. So the temperature effect is too much. As we discussed oscillator section, RT and CT. So we can calculate the amount of charging current. First of all, at CT pin, at pin number 5, when it will receive 3 volt, that time we need RT, the value of RT. So we will determine the charging current, then we can calculate the sawtooth waveform. So 3 volt multiplied by CT divided by charging current, that will the time period of sawtooth wave to adjust the oscillator frequency. So we can determine oscillator frequency F1 over RT-CT. But the old formula, the previous formula, that was F oscillator 1.1 divided by RT-CT. So it is new formula. So this formula, basically, this formula is used to determine the full frequency. As we discussed, this IC can operate in single-ended and push-pull. What is single-ended? I discussed both transistors will work together. So that function can be achieved by grounding pin number 13. If we ground pin number 13 to ground voltage, that time the oscillator frequency will full. So Q1 and Q2 will work as a single-ended PWM, as a simple IC, single-ended IC. So both transistors will switch together. That time we will obtain full frequency. For example, if we calculate 40 kilohertz, so output frequency will 40 kilohertz. But if we connect pin number 13 to V reference pin, that time this IC will shift in push-pull operation. Both output transistors will work opposite to each other, and that time the frequency will divided by 2. We can calculate it. If we calculated here 40 kilohertz, just only we connected pin number 13 to V reference, so that time the frequency will be divided by 2, or we can calculate with this formula 1 over 2 RT-CT. This is for single-ended and this one for push-pull. Discussed here single-ended application, F is equal to 1 over RT-CT, and for push-pull application 1 over 2 RT-CT. From this this oscillator can be programmed from 1 kHz to 300 kHz. Practical values for RT and CT range 1 kilo ohm to 500 kilo ohm, and capacitor value is this. So RT-CT can be determined by figure number 6. We will check the chart. This one. So here is RT, the value of the resistance, and here is frequency. At which frequency we want to program it. For example, I need 100 kilohertz. First of all, we have to go up at this point, at this cut, 0.001 microfarad, and left side about 10 plus kilo ohm. resistor. And if you want to use at 50 kilo ohm, then we have to see here. If we want to use this capacitor, so that time 0.01 microfarad capacitor, this one, and then the resistor will less than 10 kilo ohm. Or if we use this capacitor, then the resistor value will increase. At 100 kilohertz, we have to use approximately near about 10-15 kilo ohm. But for 50 kilohertz, that time the resistor will more than 50 kilo ohm, but the capacitor will same. So combination of RT and CT will use to determine the frequency and set the oscillator. Then we have dead time control. Dead time control can be adjusted by combining these two resistors R1 and R2 and its maximum percentage on time. Each output will 45 minus 80 divided by 1 plus R1 R2. So it will adjust the dead time control between the both two channels. Then we will compare TL494 with SG3525. SG3525 is also the same oscillator, but the output in switching stage. Here we can see it. We have open collector, open emitter, open collector, open emitter, TL494. And if we see 3525, so 3525 have totem pole output, 3527 totem pole output. But 3525 and 3527 have different logic levels, different voltage levels. This is its normal off condition. When it will on, it will give high voltage. But this one normally high. When it will turn on, then it will give low voltage. But its switching voltage level is different to each other. But this IC can be programmed independently by collector or emitter. We apply VCC voltage. We can apply switching voltage separately and VCC voltage separately. But if you connect the same voltage for switching and chip biasing, that is also can be utilized. When we apply VCC voltage, so that time this IC will give a 5 volt reference. Here pin number 14, pin number 7 is grounded. So this reference will be also programmed to internal amplifiers and its PWM section. Here we have RT and CT. So RT is used to charge this capacitor. First of all, this capacitor will charge when this pin will reach at 3 volt. That time its internal oscillator section will discharge this capacitor internally. First it will charge using this resistor, then it will discharge internally. So it will make ramps, it will make switching. So this charging and discharging, so charging is linearly, but it will make a sudden discharge, then charge linearly, sudden discharge. So this sawtooth wave will used to produce clock signal from here. So it will generate square wave clock signals. And here we have dead time comparator. So dead time comparator will allow the time gap between both channels. Then we have feedback section here. So its feedback section is independent. We can program inverting or non-inverting input for feedbacks. We can apply standard reference to any input and we can sense the feedback from any pin. So this IC can be utilized in any way. Then we have feedback compensation here. So it will adjust the gain of operational amplifier. Here we have feedback output control. When this switching oscillator will switch and there is a difference between error amplifier input pins, so PWM controller will adjust its pulse width modulation and it will apply to this flip-flop clock. But if this pin is connected to ground, at that time this portion will be flip-flop will disabled, and at that time it will directly operate the both transistors at the same time. But if you connect this pin to positive, it will enable these AND gates. At that time this flip-flop will work and we will switch these transistors time to time, one by one. When this will on, this will off. When this will on, because the Q and Q bar outputs of this flip-flop are opposite to each other. So output will opposite to each other depending upon the input cycle. It's also the same diagram for, but it is same for TL494 and 495. TL495 just have 39 volts in the reference here inside, and 495 have also a steering input. 495 have an additional steering input that is additional to 494. Other circuit will remain same. So here it is timing signals. First of all, we see, as I discussed, this charging and discharging of RTCT. Then we have feedback signal also here. Then we have dead time control between channels. So at each cycle it will generate one pulse. Its internal flip-flop circuit will generate one pulse. So output flip-flop will work in this way, opposite to each other at each cycle. And output of Q1 and Q2, when this output control is set to V reference pin 5 volt, at that time each output transistors will opposite to each other. If this is high, this is low. This is low, this is high. This transistor Q1 will high, Q2 will remain low. So both transistors will work opposite to each other. At the receiving feedback, this dotted line, it will adjust its duty cycle. We can see as that feedback is increasing, it is adjusting its duty cycle. But the both transistors will switched opposite to each other. If it is high, this one is low. So it is maintaining its on time vs off time. This is the second condition. When the output control pin is connected to low, connected to ground, both transistors will work together. And in that way also it will adjust its duty cycle. We can say here it is high, feedback is high. So feedback is high, that time the duty cycle is low. When the feedback is going down, it is increasing the duty cycle. When the more down, it is increased maximum duty cycle. So it is its work phenomena. At that time the flip-flop will disable, so both transistors will work in parallel mode in single-ended condition. In this way we will receive full frequency, and here the frequency is divided by 2. Here it is single-ended. When the pin number 13 is connected to 0 volt or maximum 0.4 volt, at that time the both transistors, collector and both emitters, will come in parallel. We can use only one transistor, or we can use the both transistors together by combining collector to collector, emitter to emitter, so it will work as a one switch. So at that time we can take maximum 500 milliampere. If the output control is connected to 2.4 volt to V reference, minimum amount of voltage will 2.4 volt and up to V reference 5 volt. That time every transistor will work independently in push-pull condition. This one is single-ended and it is in push-pull condition. In this case we will receive maximum 250 milliampere, but normally it is 200 milliampere. In this case 400 milliampere, but maximum 500 milliampere. The common emitter configuration for designing the transistors network: 15 volt. If we apply 15 volt to collector, normally when the transistor is off, there is no output. At that time this pin, this is the output pin, so it is high. So when it is high and we apply a signal, when this internal switch will on, at that time this ground will connected internally to this, and here is pull up resistor, so this level will go down. So this maximum level to minimum level, this time is called fall time. From 90% to 10%, it is called fall time. It is the switching time in each electronic component. So rise time, fall time, and when the signal will arrive at base, we will receive low output level. Then when signal will disappear, then it will take some time to rise up to maximum level. So here it is, emitter-follower condition. In this way we applied a pull-up resistor, 68 ohm 2 watt resistor, and here just only applied 15 volt to collector, and emitter is connected to one capacitor, and 68 ohm resistor is here now. Before this, 68 ohm resistor was connected in series with 15 volt, but now it is connected in series of ground. So normal condition, we will take low output. When this transistor is off, we will take ground voltage. Here we will take, when this transistor was off, we were taking maximum output high. But here when it is off, we are taking low voltage. When it will turn on, we will take positive voltage. Why? Positive voltage will switch from this point to output side. When it will turn off, that time the output will also drop. So here it is fall time. In this condition, the fall time will considered here, but here fall time is here, rise time is here. Because rise time, the time from minimum level to maximum time, that is excluded from the switching cycle. So its working window will from 90% to 90%. So this cycle will be considered for switching. This is switching time, this is rise time, fall time. So here is error amplifier biasing. As we discussed, this IC can be programmed in any condition. We can program in this configuration. We are configuring a non-inverting input to sense the feedback. So feedback applied here, and this pin was connected to the reference pin. So this IC will work, and in this condition it can also be programmed if we connect non-inverting pin to ground, and inverting pin can be programmed to sense output. So here is an example for single-ended operation. So it can be used as a buck regulator or anything. So pin number 13 is grounded here. So both transistors will work together. We can see this emitter is grounded here, this emitter is grounded here, this collector is connected to this point, and this collector is connected to same point, and 270 ohm base resistor, current limiting resistor, and we have 100 ohm resistor to adjust feedback base biasing. So it will drive these transistors. RTCT is connected here, dead time control, soft start section, and here is feedback section. So it will sense the feedback from this point. And here is, we can see it is connected as a voltage reference as feedback reference as well, because this is voltage level. So this voltage level is connected to pin number 1, and error amplifier number 2 is used for current sensing. We can see here is a load, and in series of load there is a 0.1 ohm resistor. So load will drive from this resistor. So dropped voltage across this resistor will apply to this IC to sense the output current. Here is current limiting resistor, load 0.1 ohm resistor, and the current flowing from output section to load through this resistor will cause to drop voltage here, and this amount of this dropped voltage will apply to this error amplifier number 2, pin number 15. So it will amplify the error, and it will sense, and it will give feedback how much the load current is now running. So pin number 16 will apply to reference pin to set a fixed reference. Then we have soft start section. To give a soft start to this IC, it will limit the turning on time in first pulse, pin number 4 voltage. First it will high, then it will charge the capacitor, and it will low, and that time it will give a on time from this point. This is soft start, and it can be calculated. So here is master slave operation. If you want to use these ICs for 3, 4, more than 2 ICs, so in first IC we will determine the RTCT value and we will fix its frequency, but for the other we will not use CT and we will not use RT. If we use 3 or 4 or 5, how much we need. Just only we will connect CT pin to all CT pins, so all oscillators will slave to this master IC. If this IC is working at 100 kilohertz, all ICs will work at the same frequency. So it's its simplified diagram, RT-CT section and dead time control. Here we have PWM comparator, and this comparator will check the clock signal and it will monitor the voltage and feedback, current feedback. So error amplifier number 1, error amplifier number 2, both levels will apply to this comparator, and then it will apply switching and it will control the duty cycle, and then it will apply to this flip-flop circuit and output control circuit. So friends, I hope so this video is informative. If it is informative, give a thumb up. If you have not subscribed my channel, subscribe it, and if you want to watch my future videos, you can press bell icon button if you want.